it says it's going. Okay. So thanks you guys for being here for the review. I look forward to hearing what questions you might have. What I want to do, as usual, to start with is just to kind of tell you about the format of the test. And then I can also start by answering some of the questions that were posed to me through email. And then certainly I'll give you guys a chance to ask any questions you might have as well. So this test, I think, should be similar in length, or in other words, the amount of time it takes you to finish it. So hopefully that can help you a little bit thinking about your planning. You have a 4-hour window, just like you did last time. And again, there are a lot of materials available in that module through Canvas to help you prepare for the test. So hopefully you guys have already discovered those things. There's the PowerPoint, which helps you with choosing a test. There's worksheets which help you with solving the problems. And then also you can go ahead and click on the formulas so that you'll have the formula sheet that will be made available for you for the test. This test is formatted, it's got 6 multiple choice questions. All 6 of those are asking you to choose the test. So basically, because that's one of the most important aspects of this unit, it's a way for me to just evaluate your ability to do that again. Then there will be 4 problems to solve. And if you guys have already watched the review from last year, then you're hearing this again, but there's nothing tricky about that. You've learned to do 4 different types of hypothesis testing. There are 4 problems. Nothing tricky, you do the math, all right? If you end up doing the same type of statistical test more than once, you're making a mistake, okay? For each of those tests, obviously you're gonna have to solve the problem. That's part of it. And, make sure you send that to me with your exam, because that's where I'm able to give partial credit. But what's easiest for me actually is that at the bottom of each sheet of paper, I ask you to do 4 steps for me. Step 1 is tell me what test you're conducting. So if you say you're doing independent samples and I know it's a dependent samples t-test, then I know we've got problems already, and I'll just go right up to your work and start trying to deal with that mistake. But you identify the test you're doing. Step 2, you tell me what the critical value is that you're comparing to. So that'll be either a t-crit or a z-crit. Step 3, you're just going to write what the decision is. Am I deciding to reject the null or to fail to reject the null? And then step 4, you'll write your concluding statement. Now, if you haven't done the SPSS assignment yet, in some ways it'd be a good idea to do it, because you do get a lot of practice with writing those concluding statements. The concluding statement needs to include the independent variable, the dependent variable, the value of the test statistic that you solved for, right? So if it's a t-test, it will also include degrees of freedom. So it would say, there was a significant difference in performance as a function of the treatment. So performance is the dependent variable, treatment's the independent variable. Told me it was significant. You got to have significant or not significant. And then a comma. If it's a t-test, it would be t parentheses degrees of freedom equals, and you tell me the test statistic that you solved for. And then you put comma. The way I just said it, I said it was significant. So if it's significant, then it has to say comma p less than 0.05. And then if it's a t-test, you'll put one more comma and you'll tell me if it's one-tailed or two-tailed. So for the z-test, everything's the same as what I just said, except of course you don't need degrees of freedom. And that's it, okay? So you don't have to write out a null hypothesis. You don't have to write out an alternative hypothesis. You don't have to write the hypotheses in symbols. All you have to do is be able to write the concluding statement at the end, okay? It might help you to write that because that's the way you've practiced it, but it's time consuming. And if you can write the conclusion statement right, then I know you understand how to do the null and alternative. Again, the formulas are available. You can already get that through Canvas, the ones that you're allowed to use. I am not giving you the formula for sums of squares or the mean. I assume you guys know how to calculate a mean. But I'm not giving you the sums of squares for the formula for sums of squares. So if you don't already have that memorized, you need to make sure you go back and learn it. Part of the reason for that is because when we move into ANOVAs next week, you're going to be calculating sums of squares like a bazillion times. So you may as well go ahead and learn it. When I say the sums of squares formula out loud, I say the sum of x squared minus the sum of x all squared. And when I say all squared, I'm reminding myself to put parentheses around it before I square it, over n. So that's how I say it out loud. I say the sum of x squared minus the sum of x all squared over n. So sum of x squared is by itself, sum of x all squared over n. That's the formula. Okay, so just go ahead and make sure you know that. One of the questions I got was if the exams are cumulative. They are not cumulative purposefully, but they are cumulative because everything you're learning builds up to the next section. So I'm not going to specifically ask you any questions about standard deviation, variance, sums of squares, means, what we did before. But obviously, you have to be able to do that to do the work that we're doing now for hypothesis testing. There are no questions on the exam about SPSS. That's a completely separate application part that we're doing through the computer assignments. And there are no questions about effect sizes or confidence intervals. Not multiple choice, not conceptual, nothing. I'm sorry, I'm glad I just said that, because there is going to also be one conceptual question. And I'll tell you in advance that it will either be about statistical power or about the various forms of error. Those concepts are things that I really would like you guys to understand and be able to take with you going forward. Nobody will remember how to calculate a t-test by hand. But what I'm hoping you get from calculating them by hand is just this really good understanding of what statistical tests are. And that is, and this is important for me to say, that every statistical test that we're calculating has the same general format. In the numerator goes a difference between either the mean and some standard, which might be 0, or some known value like a 50-gram bag of pretzels, right? The numerator is always the difference between a mean and some known value. That known value could be another sample mean, right? So when we do independent samples t-test, the numerator is one mean minus the other. When we do z-test, it's a mean minus some standard that we're comparing to, some constant. And for every statistical test that you conduct, the denominator is always going to be some measure of standard error. And that measure of standard error is going to be a measure of variance or standard deviation divided by the square root of n. Or I should say relative to sample size, because it's not always divided by the square root of n as we go forward. But it's essentially variance relative to sample size. And so one of the questions that one of your classmates posed was, okay, so if you asked us a question about how we make the t bigger or the z bigger, you guys had a lot of questions like that on the quizzes, I know. Those are really important conceptual things for you guys to understand, because if you want to make the test statistic bigger, all you need to do is think about what the general formula looks like. The numerator is the difference between the mean and whatever you're comparing it to. You guys who are going to be doing your own research in the future, EDD students or thesis master students, if you want to make sure that you get statistical significance, you've got to make the difference between your groups as big as possible, right? So rather than compare 10-year-olds and 9-year-olds, boy, I'd be smarter if I compared 10-year-olds and 4-year-olds, right? Now, that might be a silly question. It might not be meaningful, but you see what I mean. If I'm doing an exercise question, it'd be better to compare 100 jumping jacks to 0 than it would be to compare 12 jumping jacks to 11 jumping jacks, because my numerator is the mean difference, and I want to make the groups as different as possible. To make this test statistic big in terms of the denominator, you want to keep variance small, because in the denominator is another fraction, and variance is on the top of it. So if I can reduce the top of that fraction by reducing variance, then I'm going to increase my test statistic. So you guys who are thinking experimental design, that means you want homogeneous groups. You want everybody to be as like as possible. If I want everybody to do 100 jumping jacks, how do I make sure that's a pure 100 jumping jacks? Well, I count it. I measure it precisely. And I also measure the dependent variable precisely. And that keeps variance smaller. Some of you guys who do studies recruit participants so that they're very similar. My doctoral student, we're doing a study here right now, and we had decided that we were going to recruit people who are between 50 and 70 years of age. The reason we chose sort of that's not narrow, but a somewhat narrow age band was because we want those people to be as similar to each other as possible. We're having a hard time getting enough subjects, so he just asked me if we could expand it to 50 to 80. Well, we certainly can, but the implication is that the sample won't be as homogeneous, so the variance in performance is likely to be larger, which means it's going to be harder to find statistical significance. But the reason we're expanding the age range is because we can't get enough subjects. Well, n is the last piece of this formula, right? The bigger n is, the smaller that overall denominator, the standard error gets, which means the bigger my test statistic gets. So the reason we're willing to sacrifice a little bit in variability by going to 50 to 80 is because right now we only have 16 subjects. Well, if I can get 30 subjects, that's going to have a huge impact on my standard error by reducing it, which is going to increase my test statistic. So those kinds of, those conceptual questions in the quizzes, like I love those because I hope that they're helping you guys to think about those conceptual things that are really the things that matter the most for you guys going forward. The other questions I had that people wrote in, this is a really good one. So when you do, let me think how I want to start this. If you're doing two-tailed tests, life is easy because your critical value is going to have a positive and a negative. You're going to put 0.025 in one tail, 0.025 in the other tail. You'll have a critical value to set off that upper little piece of the curve, and a negative critical value to set off that lower little piece of the curve. When you solve for t or z, then you'll just find out if it's in one of those tails. But when you have to do a one-tailed test and you put everything in one end, you have to make sure that whatever values you're using to calculate that t or z are in the right direction, right? So if you are predicting, let's say it's a dependent samples t-test makes it even harder, but let's do that. If we can understand that, will be great. With a dependent samples t-test, say you're comparing a treatment to a control condition. If your hypothesis is that the treatment is going to increase the scores, right, is going to increase the scores, then the way I would do it is I would put my tail on the positive side of the t and use a positive t crit. And when I subtracted, I would make sure that I subtracted treatment minus control, because I'm expecting the treatment score to be bigger than the control score. So when I take treatment minus control, a positive difference is in the direction I'm predicting, and that's what I'm going to compare to my positive t. Does that make sense? Can you guys give me head nods? If that makes sense, I almost don't want to say it the negative way because it's just more complicated. But the thing is if I pick if I say that the treatment's going to be bigger than the control, or cause an improvement, or cause scores to go up, and I use a positive t critical value, if I subtract in the wrong direction and say control minus treatment, so that when the treatment is bigger than the control, it comes out a negative number, then even if I'm in the right direction, my mean is going to be negative, and I'm going to be way over on the wrong side of the curve. I'm not comparing it to the proper criterion value. So it just has to make sense that if you're predicting a positive change or a positive difference, you use your one tail on the positive side. If you're predicting a reduction or a decrease, or that one score is going to be less than the other, then you use a negative t and you subtract in the way that when the means are going the direction you predicted, which is a reduction, that it comes out as a negative number. Does that make sense? Okay. And you guys, do you have any questions about that, or does that feel okay? Okay. I think, unless I'm missing something, oh no, I'm sorry. I got two more things that came in from your classmates. One is to, oh, that's right. Okay, so somebody wrote, I'm sorry, so this is following up on what I was just talking about, the one tail. Okay, so if I am saying that my treatment is going to cause an increase compared to my control group, and I subtract treatment minus control. When I subtract, if it's positive, that's in the direction I predicted, right? Treatment is bigger than control. So if treatment's a 10 and control's an 8, I take 10 minus 8 and I get a +2. Treatment was bigger than control. That's what I predicted, okay? And I have a positive t. But if, when I take treatment minus control and I know I'm doing it in the correct direction, and it comes out negative, then that means I was completely and totally wrong. Everything I thought was wrong. The treatment group actually caused a decrease, not an increase. And so my t that I calculate is going to be negative. So there's no way it's in that little positive tail. I've failed to reject. And the reason that's important, I think conceptually, is that after you guys finish taking this test, you'll probably never do a one-tailed t-test again in your life. And the reason is because people are a little bit afraid of that. I mean, we might know the direction we expect things to go, but we usually actually just predict a difference or a change. We often don't predict the direction. And when we do ANOVAs in the next unit, you can't actually predict a direction. So it doesn't happen very often. And usually you wouldn't be that wrong. If you think the treatment's going to help, it would be very atypical for it to actually hurt and have a negative value. When you do it in SPSS, the direction of the T is completely and totally determined by the order in which you drag those variables into the little box that says which variables are you comparing. If you drag them one way, it's going to subtract in one direction. If you reverse how you drag them, it'll go the other direction. And so the direction of your T is just determined. And it's a little bit, I don't like that. It's a little bit hard to know. You have to kind of get used to it and play with it to see which way is it subtracting. But when you do t-tests in SPSS, they're always two-tailed. SPSS doesn't run one-tailed t-test, so it doesn't matter if it's positive or negative. It only runs two-tailed. Okay. Let me go next to then the question about how you choose the test. So in this unit, the options are a z-test, a single sample t-test, a dependent samples t-test, or an independent samples t-test. Of those four tests, or to decide which of those four tests you're using, the first step is to figure out how many sets of data do I have, or how many samples of data do I have. If you only have one sample or one group of data, then if you think of it sort of as a flow chart, you know that you're over here on this side where you're doing a z-test or a single sample t-test. With the t-test, it's right in the name, single sample t-test. There's only one sample. With the z-test, it's also single sample, so you could call it a single sample z-test. Once you know that, then the decision about z or t depends on if you're given the measure of variance or standard deviation for the population. If you're given sigma squared or you're given sigma, that's the measure of variance for the population. And if you have that, you would always choose the z-test because the z-test is precise. If you're not given sigma or sigma squared, then you must be given S or S squared, which is the sample standard deviation or the sample variance. And you would know, I don't have sigma squared, this has to be a single sample t-test. And a t-test means I'm estimating variance from the sample variance or standard deviation. Okay? So that's how I know I keep doing these air things. You guys have to stick with me. But that's how you know if you're on the left side where it's one sample between Z and T. If you were given both sigma and S squared or S, you would choose the z-test because it's precise. If you're given sigma or sigma squared, use it. If you don't have it, you have to estimate it. Then the other two are the dependent samples t-test and the independent samples t-test, which means that you've got two samples or two, let me not say it as two samples, two groups of data to start with. So your next question is, are these groups of data related to one another? Are the people who provided that data related to one another in some way, or are they independent of one another? If they're related, it is typically going to be things like it's a pre-test, post-test, so they're not just related, they're the same person. Or it's a treatment day and a control day in random counterbalanced order, but it's the same people doing the treatment and the same people doing the control, so it's the same person. When they're related, which is a little harder sometimes to judge, it could be like if it was twins. If you took identical twins and randomly assigned one to the treatment condition and one to the control condition, they're different people, but they're so closely related genetically that we would treat them as a related sample and do a dependent samples t-test. If they're independent, the purest way of independent is that they're not related, they don't know each other, they're completely different people, And so you got one group of completely different people in one sample or in one condition, and the other sample is completely different people. They're not related, they don't live together, they're not twins, they're not siblings, they're not husband and wife, they're people who don't even know each other. That's the best way possible. So once you know if it's a dependent samples, that they're dependent samples, then obviously you're doing a dependent samples t-test. The reason I flip the order on those chapters is because once you calculate the difference scores, then essentially you're doing it exactly like a single sample t-test. because you've taken the 2 data points per person and created one sample of data, which is your difference scores. And so then everything you do is essentially the same as a single sample t-test. If it's independent samples t-test, that's when, as you guys know, there's some harder math, because you have to remember that you need the pooled variance, the S subscript P squared. It's the easiest to start with the pooled variance. And then you have to do your step from that pooled variance to get your standard error using that slightly more complicated formula. Okay, any questions about that? Okay, the last thing that somebody brought up in an email was understanding differences in errors when you're hypothesis testing. This is, again, something conceptual, but it would just be awesome if you guys had this and kept it with you as you went forward. A type 1 error, the way that I remember it, is just to think that a type 1 error is the most likely thing, the most likely error that a experimenter might make. And that is, okay, let me rephrase it. Let me pull back from that. Not the most likely, the most egregious, the worst error that I could make. I got to totally strike that from your notes. I see some of you writing, strike that part. It's not the most likely. The likelihood of a type 1 error is fixed, it's 0.05, right? We set it in advance as 0.05. So it's the same every time we run a study. But it's the worst error that we could make, because that's the error where we get everybody all fired up and we say, look, my treatment makes a significant difference in whatever outcome we're looking at. And so everybody gets all fired up and they're going to start doing whatever you said. And so it's a bad mistake to make if it's not true. If you guys can switch your focus to thinking about sort of a medical perspective, if I run a drug trial and I tell you that this drug has a significant benefit for blood pressure, it can reduce your high blood pressure and it makes a significant difference, then I start marketing it, then people are spending a lot of money on it. If it's a pharmacological intervention, it probably has side effects. So I might be telling people that it's going to help, and they might be suffering through side effects and paying a lot of money. And then if later we find out it didn't help, well, that was a horrible mistake to make. A type 2 error, in some ways you could think is bad as well, but it doesn't cause people to change their behavior. A type 2 error is when we fail to say something is significant when in fact it was. And this is when, so we run our intervention, and you can think medical again, and it's a pharmacological intervention, and I have a bunch of people take this medicine and I follow them over time, and in the end I say, you know what? The drug did not have a significant effect on whatever I was measuring. Well, if that happens, of course, nobody's going to start taking the drug because it doesn't work. Now, it's a missed opportunity, perhaps, if we fail to find significance when, in fact, it does have an effect. But it could also be that it's just such a small effect. Think numerator over denominator again. It's such a small effect that it's not significant. And if it's that small, then why would I tell people to run off and start taking it? So type 2 errors typically occur, we would imagine, because it's a small effect, because it's large variability, or because we have a sample size that's too small. And if you think about those 3 things, those are exactly what goes in the test statistic. Okay, so the type 1 error we think of as the worst error you could make. The type 2 error is also not good, but it usually doesn't cause harm because you don't get people to start doing something that doesn't work. It's more like a missed opportunity. And then power is where we want to be. Power is where we reject a null hypothesis when, in fact, we should have rejected that null hypothesis. And so we say our treatment works, and in fact, it does work. So people start changing their behavior, and they start seeing the benefits. I think that's it from questions that I got emailed in. If you guys, it's the same message that I've had in the past. Please take advantage of everything I've provided for you. You have worksheets for every single chapter. So if you want to go back and repractice those, that does remind me. I'm sorry. I thought of one important thing to say. I know, this is really important. We haven't done z-tests for a long time, like 4 weeks, right? Hypothesis testing with the z-test. Don't forget that z-table looks really different than the t-test table. So the t-test table to me is actually really easy. There's the rows across the top where it says, are you in a one-tailed or a two-tailed? You find the degrees of freedom, you line it up, and you get your t-crit. But remember, with a z-test, you're looking for the alpha or the 0.05 to be in either one tail or two tails. So just make sure you're practiced with that table. You go to the column where it says the proportion that's in one tail. If it's a one tail test and you put 0.05, okay, let me rephrase that. The proportion that's in the tail, and if it's a one tail test, you put all 0.05 in the tail. If it's a two tail test, you split it and you put 0.025 in the tail. So when you come down, you'll be looking for 0.025, and that's your Z crit, a plus and a negative. Does that make sense? Sorry, I've misspoken a couple times this morning. Okay, I just got a question in. Can you guys hear my phone? Sorry. Let's see if I can. Okay, I'm gonna go away. I can't remember how I do it in the test. It should be extremely clear if it's 0.05 or 0.01 for alpha. I think I say it at the top of the whole exam, like assume 0.05 for all tests, assume normality, assume you meet the assumptions for all the tests, and just go forward with 0.05. In real life, the way that you decide between 0.05 and 0.01 is how risky is it to make a type 1 error? So again, if I go back to these medical examples, if the drug that I'm testing has serious side effects and is extremely expensive, then I would probably set my alpha at 0.01 because I really don't want to make a mistake. If it's sort of the type of testing that we typically do in kinesiology, not kind of pharmacological type of research, more behavioral type of research, we probably would set it at just 0.05. That's the standard that's used, across the board by almost everybody. I will mention you could set it at 0.10, and we do that sometimes if we're doing pilot work. So if we're doing pilot work and we want to just sort of like signal detection, does this do anything? Well, I might set alpha at 0.10. You guys hear me right? 0.10, making it bigger than 0.05, because I just want to see if anything's there. I want to give myself a chance to see if anything's there. Then I would have to follow that up with testing at the standard of 0.05. And if I really wanted to get stringent, I would go to 0.01. Okay, so that's the conceptual answer. The practical answer for the exam, which I know is most pressing for you guys, is I'll make it really clear. And I think I only use 0.05. I can't promise that, but I think that's what I did. Okay, anything else? So take advantage of what's out there. Use the review sheets. Use the PowerPoint. Use each other to help, ask questions. Certainly I'm still available. Send me emails. We can talk by phone or however you need to get you the answers. Make sure you're prepared for the test. We keep rolling right after this. The week of spring break was awesome, but we got to keep moving. So make sure you don't forget about the SPSS assignment as well. And other than that, I just hope you guys do great. And let me know if you have any questions or problems. Thank you.
Thank you.
Yes, thank you.
You're welcome. We'll see you guys.
Thanks.